So yeah, so just in case anyone in the audience is not already familiar with quantum computing, the basic idea is that normal computers work with bits, which are just ones and zeros, whereas quantum computers work with quantum bits, or qubits, which can be a 0 and a 1 at the same time. And the technical name for this is superposition. And when you combine this with another quantum concept called entanglement, you unlock a vast number of states. But the reason that we're so excited about this is because you can use a quantum computer to solve problems that we never could have hoped to have solved using normal computers. And a perfect example is in molecular simulations. So in the upper left-hand corner, this is my favorite molecule, caffeine. It's not terribly large, but if you were to use a computer to try to simulate this, a classical computer, you could do it, but it would take a computer about 1 to 10% the size of the Earth. If you were to simulate a slightly larger molecule, say penicillin, it would actually hit the theoretical limit of what you could do because it would require a computer the size of the entire universe. And so for these reasons, we'd like to think of some other way to approach these problems. And quantum computing can solve these using a very modest number of qubits, actually just a few hundred. And as I'll explain, the roadmap for quantum computing makes us believe that this is a very much requirement that we could achieve in the next few years. The amazing thing about this is that we already have quantum computers. This is not a science fiction buzzword. It actually exists, and we know of hundreds of quantum computers just in the Western Hemisphere alone. And there are lots of different approaches to building these quantum computers. Some of them include superconducting, which is an approach used by IBM, and I know that you're very close, being an IBM hub here, and Rigetti and Google. There's the ion trap approach used by IonQ and Honeywell. There's photonic, and there's several others. And it's not immediately clear which technology is best. Each seems to have their own advantage and disadvantage. But the fact that we have so many paths towards scaling feasible quantum computers makes us very optimistic. Many of you are probably familiar with Moore's Law, which has shown over several decades that classical computers have been able to double in power every 18 months or so. Quantum computing is on a much faster trajectory. So the blue line shows the progress just made by IBM, and they've been able to double the quantum volume every 12 months or so, if not sooner. The orange line is the progress made by Honeywell, and they've been able to increase the quantum volume by a factor of 10 every year. And they believe they can continue with that for the next several years. So the next several years should prove very exciting. Both IBM and Google predict that within 3 years, actually 2.5 now, they should have 80,000 qubits, and within 10 years, they will have 1,000,000 qubits. So that's the power that we expect to have in the next few years. So I'd now like to say a few words about the company that I work for, Cambridge Quantum. So we're about 7 years old, and as some of you might have heard earlier, we have a pretty unique origin story. Our founder and CEO, Ilyas Khan, he was chairman of the Stephen Hawking Foundation and got to know Professor Hawking, who advised him in 2014 that he thought quantum computing was really going to take off and that Ilyas should get into this business. So fortunately, he listened. So this makes us one of the oldest quantum computing companies, only 7 years old. We have grown quite a bit. We now have about 150 people, most of whom are in the UK. So this is why we came out of the University of Cambridge. So we really are based in the UK. There's a few of us in the US. I think there's about 7 of us all on the business development team. I happen to be based in Portland, Oregon. There's about 5 people in Tokyo, and we plan to soon open an office in Munich. We have focused exclusively on quantum software for the past 7 years. And so because of this, we've established partnerships with all the major quantum hardware providers like IBM and Honeywell and Google and Microsoft and such. We've become especially close with IBM and Honeywell. They invested in us, and I'll mention some of the advantages of that in a second. One major thing that you might have seen in the news about 3 months ago is that we are in the process of merging with Honeywell's quantum group. So Honeywell is spinning out their HQS, Honeywell Quantum Solutions team. We are merging with them, and that should be complete in the next few weeks. So that's very nearly done. And then we will likely go public after the new year. I really don't know any more details than that. I'm not on the team, but that is, as far as I know, the plan. So in terms of the type of quantum software that we develop, there's 4 different areas here. So there's the quantum development platform called Ticket. There's our chemistry application called Human. There's machine learning and also natural language processing. And then finally, our cybersecurity division. So I'll briefly mention each of these in turn. To understand where we fit into the stack, so this is the quantum stack. It's pretty similar to how a classical computer works. So on the top of the stack here, we have any application. So this is something that someone would actually do to solve a problem. The application, of course, depends on these different algorithms. So these are actually the mathematical procedures that you use to solve them. Those all depend on compiler or software development kit, which in our case is called Ticket. If you're curious about the name, our first CTO, his name started with a T, and then it was a quantum system, so it was a KET. So it was his KET, yes. So it's pronounced Ticket. So Ticket is the interface between the quantum algorithms and your hardware or simulator. So to understand how this works in more detail, the first thing to understand is that right now, we sort of have an embarrassment of riches. There's a lot of different quantum software languages. Each one was, of course, developed by a particular team. So Google developed Cirq, IBM developed Qiskit, Microsoft has Q#. And of course, if you use that language, you can run it on that particular platform. But the problem is that there hasn't been any sort of universal compiler. If you switch platforms, you have to completely rewrite your code. The languages are similar, but they're not identical. And so this is a big hassle. This is the reason we developed Ticket, because it's both language and platform agnostic. You can write your language, you can write your program in any of these languages, and you can execute it on any of the hardware platforms seamlessly. So you actually just add one line to your code saying, I want to compile this using Ticket on this platform. And Ticket knows all the details of the different hardware platforms, and it will automatically find the most efficient way to execute your program on that platform that you've chosen. So I'll go into a little more detail about that. Just to emphasize how universal this is a comparison of the backend support of Ticket compared to the other platforms. So you see that if you use Qiskit or Cirq, you could use it on that platform by that company, and then maybe a few others. But if you use Ticket, you can use it on everything. So if it's black, it means the support already exists. The shaded ones mean it could exist in the very short term. And the reason for this is, so D-Wave historically only did annealing type platforms. And of course, our compiler assumes gate-based approach. But just a few days ago, they announced that they're actually going to be moving to the gate-based approach. And Ticket, as of about 3 weeks ago, is open source. And so there's no reason why D-Wave can't now simply write an extension to support it. So in the very near future, we expect that D-Wave will have an extension so that you can run gate-based programs on it. And second is Quantum Circuit Sync. Again, they're welcome to now build their own extension. We just hadn't gotten around to it yet, but there's no reason that it can't exist. So how does Ticket work? So as I said, Ticket allows you to write your quantum program in your favorite language and then execute it on your favorite hardware. And Ticket will automatically find the most efficient way to do that. But how does it do that? So there's two steps to this. The first step is optimizing just the circuit itself. So this is the abstract quantum circuit. This has nothing to do with the hardware. The second part is specific to the hardware, and it takes into account both the way that the qubits are connected and the gates that are native to that architecture. So let's first look a little more at the first one. So the first one is just making the circuit itself more efficient. And it does this using something called the people optimization. So what it means is that it goes through your quantum circuit just locally, just looking at a few gates at a time, and it looks for certain patterns. And it has a list of patterns to look for, and then what to substitute for them. So let me give you an example. So this is a typical quantum circuit. So you have your initialization, and your operations, and your measurement, and in between you have this combination of gates. So the people optimization goes through, and it looks for different gates. So these are some of the things that it looks for. So the most obvious one is on the upper left-hand corner. So just 2 CNOT gates in a row, right? So this is mathematically identical to nothing, just the unity operator, right? Just leaving the qubits untouched. So if Ticket sees this, 2 CNOTs in a row, it just removes them. So that's very simple and obvious, right? So your program will run a little bit faster, and it's a little less likely to make an error. These other substitutions are less obvious, but if you had some time on your hands, you could check. Each one of them is mathematically identical before and after. And they've been done in a way so that the program will run a little bit faster, uses less gates, and is therefore less prone to error. So I've given a few examples here, but if you're curious to understand full set of examples and how this is achieved, this is the archive number. And so you can look up the mathematics of it. So again, this is how it optimizes just the circuit itself. This is completely independent of hardware. So the second part is focused on the hardware. And each hardware has its own idiosyncrasies. There's all sorts of constraints that the architecture has. Ticket knows all of this. And to understand how important this is, so these are 3 examples of superconducting machines. So they have something in common. They're all superconducting. But you see that the layout is very different. The qubits are connected in vastly different ways, right? And not only that, the gates that are native to these different platforms are all very different. And these may not have anything to do with the gates that you've used on your circuit, right? And so Ticket knows all of these details, and it will take this into account. And to give an example of how important this is, so on the left-hand side, this is IBM's Melbourne machine. And you see that it has at most 4 qubit couplings. So at most, 1 qubit is talking to 3 others. On the right-hand side, this is a circuit which has some 5 qubit couplings. So you see the 2 qubits on the bottom, they're talking to each other as well as the 3 on top. So naively, we might think there's no way to run that circuit on the right on the machine on the left. That's actually not true, but what you have to do is something called routing. So routing is done using moving information from 1 qubit onto the other. So you can do it, this swap operation, which is really just a few CNOT gates. But of course, CNOT gates are computationally expensive. We don't want to introduce them unless we have to. So Ticket has a built-in optimizer. So it figures out what the mapping of your circuit to the hardware is, and it takes care of the routing, trying to do it as little as possible. So it knows that this is expensive. So this is a very difficult problem, and Ticket has a built-in heuristic. It doesn't do it exactly, but it usually does a pretty good job. And so again, this is all invisible to you. You don't have to do anything. You just say, I want to run it on this platform, and Ticket will do all of this automatically behind the scenes.
Can I ask a question? Like a couple of slides ago, I just saw that, for example, when you have like not two CNOTs consecutively, but like when you have, you're like changing CNOT and the CNOT on the other way to a swap, or like even the last line, you have 2 CNOT, but you're changing into a swap gate and a CNOT. So I was about to say that like a swap gate is actually 3 CNOT. Why are you doing that? Is this like done specifically in different stuff like that you actually can swap the qubits physically? Or so I think you cannot do that, but
yeah, you're not physically swapping them, but this is, I think they're just using shorthand rather than write 3 CNOTs by hand. I think it's just shorthand for.
So that actually just increases the number of CNOTs. I was like, oh, okay, that might be something else then. I was thinking that like it should be.
They must have some metric by which this is more efficient, even though it seems to look like more gates. They wouldn't have added this unless they thought it was somehow advantageous.
Okay, all right. That's just some very specific questions. Sorry about that.
Yeah, no. These are good questions. Yeah, I don't know exactly which metric they've used, but somehow they thought this was favorable.
Okay, right.
So obviously we use Ticket for our own algorithm development. Many other groups have been using it as well. So these are some of the articles that have been written by other groups, including IBM and Google and even CERN for some of their development. And they've had very favorable results. This is a benchmarking study that was done last year. So on the left, this is benchmarking of the number of gates that were needed to implement it on different hardware platforms. And Ticket needed far fewer gates to achieve this. And on the right, this is a benchmarking study of the execution time. So of course, lower is better. The vertical axis, notice, is on a logarithmic scale. So Ticket wasn't just a little bit faster, it was orders of magnitude faster compared to some of the other compilers. And so especially in this NIST era, when we don't have that many qubits and we don't have that much coherence time, this can mean the difference between running your program and not running your program.
So what are the different bars?
I think one has to do with the mapping and the other has to do with the compression. I think.
So there's no comparison with something that's not Ticket.
Yes. So this is the IBM one. This is Qiskit, and this is Google's.
And the middle one is Ticket.
Is Ticket.
I see. Okay.
Yeah.
Thanks.
Yes. We are constantly updating it. We update it about once a month. So it automatically has the latest hardware feature support. The big news, okay, that should be September, obviously. The big news as of September 29 is that it is open source. So this was a big decision that we decided to make. We wanted to make this available for everyone. So it's obviously free, anyone can use it. All the source code is available on GitHub now. And so this means if you're a software group, you can write your own subroutines for optimization. If there's a type of circuit that you really need optimized and you have some clever idea for how to do that, you can write your own subroutine. And if you're a hardware group, you can write your own extension so that people can run programs on your machine. Obviously, so before that, we had removed all licensing restrictions, so at least people could use it however they want. And as I said, we're constantly updating it with features. And in the future, we will be adding an error mitigation toolkit, which will also be open source. We will be moving it to the cloud. So right now you download it from GitHub and you run it locally. As programs get bigger and more sophisticated, that may not work. And so we will soon be moving it to the cloud so that you can do the compilation using things like Azure or AWS. This might be more computationally intensive. It's also a little easier to do collaboration. And then finally, we're already looking beyond NIST. So we're already looking ahead to things like error correction, and we're starting to build out our teams so that when the hardware catches up, we'll be able to take advantage of that. So this is the URL. This is how you can download it right here. It's just a standard GitHub repo. So I encourage you to do that. There's lots of documentation and examples to help you get started. It's the standard pip install to do that. So you just do that for PyTicket and then whichever module you want to use, whether Qiskit or Circ or what have you. So it's completely straightforward way to install it. So that was it for Ticket. I also wanted to say a few words about some of the projects that we've been working on. I realize you're probably not going to hire us for engagements, but I at least want to explain the kind of business model we have because we're actually quite different from other companies. Most other quantum startups are consultancies. So you hire them to write a report or kind of advise you on things. We don't do that. So we're completely application driven. We don't write reports unless it's part of building an application. So the way it works is that companies come to us and they say, we have this problem, can quantum computing help us? Here are some of the bottlenecks. And so then our scientists work with them to identify where we think quantum could make an improvement in the short term. So we're not focused on things in 20 years. We want to look kind of in a 2 to 3 year time span. We formulate how to solve this problem, and then we write the algorithm. We actually execute it on real quantum hardware. And historically, we've chosen which hardware platform during the project, because of course, different platforms have different advantages and disadvantages. We are now that we're merging with Honeywell, we will probably by default run on Honeywell system, but if that doesn't work for some reason, we're still happy to use other platforms. And then finally, we assess, and we see, is this really able to scale towards commercial feasibility, or should we look in a different direction? And so we've had several dozen projects now fitting this model. And I can talk about a few, and I will now. There's many more that we can't talk about publicly, but we really do have great expertise in all the areas that I've mentioned: chemistry, machine learning, natural language processing, cybersecurity, and such. So to just quickly give a few examples of ones that we've publicly announced. So this is our chemistry application, which we call Human. So Human is one application, but every time we've had a project, we've built in some feature. So we have about 20 features now in our chemistry application. Up until now, we've been the ones running the program. So companies have come to us saying that they need some calculations done, and we've been developing Human, and we've been the ones running it. We're now about to unveil, we have unveiled a beta testing version for a few partners so that clients can use it themselves. And so we're trying to make it kind of user-friendly so that companies could just hire us to use the program themselves, and we don't need to do everything. So a few examples. So Nippon Steel hired us to work on a project for studying this metallic structure. And this is a big topic in quantum computing because classical computing has great difficulty modeling these highly correlated systems. And so this was one project. Total hired us to work on a project with carbon capture. And obviously this has a lot of implications for environmental studies and making the environment better. We're working on a project right now with Roche. Many of you are probably familiar that drug discovery is a major topic in quantum computing. And so we're working on a project for Alzheimer's drug discovery, modeling chemical interactions to see how these are molecules fit in with proteins with an eye towards Alzheimer's drugs. In terms of machine learning, we have several different applications. So unlike human, which was one, so we have several different areas. Many of our clients have been financial, and we can't really talk about that. Unfortunately, we have all these NDAs with them. Some of the ones that I can talk about, yeah, so many of our projects have been financial. A special focus of ours has been Monte Carlo simulations. So you probably know that in a lot of trading algorithms, you model the uncertainty of the markets using Monte Carlo. And there's a quantum Monte Carlo algorithm, which was believed to be quadratically faster, theoretically. A few months ago, one of our scientists actually proved this rigorously, that in practice, you can get this quadratic advantage. And so, he's now really on this speaking tour virtually, especially to financial institutions. I understand he's speaking soon at this UNC business school speaking circuit.
But the Stefan Werner's paper that you have up there, I thought they demonstrated that quadratic speed up a couple of years ago with hardware.
So my understanding is that it was more theoretical, that the algorithm itself could have quadratic speed up, but in practice there were still doubts. And then our guy Stephen Herbert a few months ago showed that this is true in practice.
Okay. I thought that Stefan and the group did it experimentally as well, but this neither here nor there. Well, I believe in it.
No, it's good that they're consistent at least.
Yeah, exactly.
Yeah, so we have a lot of expertise in machine learning, especially financial. Another thing is in optimization, and this shows up all over the place, including like job scheduling and supply chain analysis. And actually, Nippon Steel hired us not only for that chemistry project I mentioned, but also just in their manufacturing process, all the supply chain and all the tasks that have to be done. And so we're working on a project for them as well. We did a project for DHL, the shipping company. And so it was a comparison of quantum to classical. And so we were able to show that there was a promise of speed up in their shipping algorithm, in exactly how they track which packages go where. And then in AccuVP, this was a classification problem. Different things. So we have this whole host of machine learning projects. So finally, and this is actually something which is kind of based in Durham. So Crown Bio is a subsidiary of JSR Life Sciences, and they happen to be based in Durham. And this is a project in which they looked for the effectiveness of different cancer medicines based on someone's genetic makeup. And so you're probably familiar with this idea that people respond differently to different drugs, of course. And so you can check this genetically. And so this is checking the correlations. If someone has this gene, how effective is a drug? So for one gene correlations, you can do it classically. That's no problem. For two gene correlations, it's difficult, but possible. But for three genes or more correlated, it would be impossible to do that on a normal computer. And so the idea is what degree correlations can we look at using quantum computing? And so this is a project we're doing right now with them. So the final type of machine learning that I want to talk about is in natural language processing. So many of you are probably familiar with this, things like Alexa or Siri. So there's a structure to how we use words and convey meaning in sentences. And it turns out that structure very nicely translates into quantum computing. And the team, basically the only team working on this was based at Oxford. And about a year ago, we just hired the whole team. And so they're working for us now. And just last week, they announced that they've introduced this open source quantum natural language processing development kit called Lambec. And so Lambec is now free and available for anyone to use. So it's not a program itself, it's a development kit. So you can write your own quantum natural language processing algorithms. And again, it's free and open source, anyone can use it. This is kind of redundant because I know you're at IBM Hub, but if for some reason you didn't want to do that, we're also a hub because of our close relationship with IBM, and so we're authorized to resell access. If you were interested in using ion trap approaches, of course, now that we're merging with Honeywell, we'd be happy to connect you with the sales team to use their hardware.
Can you tell me about the availability of the ion processors, trapped ion processors cool. You know. IBM, of course, as you know, has a order 20 that are on the network.
Yes,
I can imagine that if somebody just had one or two, your queues might be much longer.
it is a long queue. Yes, I
Yeah.
don't know how many they have. It is a long queue, and I've raised the point that academic groups would like to use it, and maybe there could be some special program, and they're considering that. But right now, yes, there's quite a long queue.
I see. And it's primarily your collaborators there, yeah.
We're not the only ones using it,
Yeah.
but primarily us, I think, yes. Yeah.
Okay, no,
Yeah.
thanks.
So the final thing I wanted to talk about was cybersecurity. And it's funny, if there's one thing that people know about quantum computing is it has something to do with hacking. So yes, there is a threat, and this comes from the fact that quantum computers can easily directly undo the algorithm used for a lot of encryption called RSA. Even though quantum computers can't do that today, there's indications that it could happen in just a few years, and there are rumors that hostile governments or bad actors are archiving things right now so that in a few years they'll be able to decrypt things. And so that's why it's strongly encouraged that people make this upgrade to quantum-proof cybersecurity today. Whatever type of cybersecurity you're using, you have to use keys. So these are the mathematical keys that you use to encrypt or decrypt your information. And the thing is that this often goes overlooked. People don't really think about where the keys come from. Oftentimes they use only a pseudo-random number generator, which is really just software that your computer runs, and it produces numbers which casually look random, but they're not at all random. There is a formula, and this has been exploited in the past. Now, of course, it's possible to generate truly random numbers using a quantum computer. You just prepare a qubit in a 50-50 state, and you measure it, and you'll get a 0 or a 1 with equal probability. So that's very simplistic to do. The problem is that you have no way of knowing if those numbers really are random, if someone isn't tampering or eavesdropping. Because if all you get is a string of zeros and ones, you have no idea where it's coming from. And so for this reason, we've developed this approach called Iron Bridge. So Iron Bridge uses quantum technologies to produce a string of random zeros and ones, but it does so in a way that you can prove mathematically that no one is tampering or eavesdropping. And to understand how this happens, okay, that's supposed to be an animation, which, okay.
Oh, you probably have to put it in display mode.
Yeah, okay. Oh, yes, that's actually exactly, yeah. Okay, well, it's fine. I'll just,
You could try it to see.
okay, you can try that.
We just had some display things before. We'll try and see what happens.
Slideshow. Oh, whoops, that was my mistake.
Yeah.
Yeah, it's just not showing on, it looks like it's not showing on the, on Zoom.
Oh,
That was a problem that we had before.
Yeah.
Using it.
yeah. Yeah. Okay,
Yeah.
well, I'll talk the viewers at home through this. So you have a source of entangled particles. We'll just call them qubits. So because they're entangled, whatever state they're in the same state. They're random together. And these qubits are measured by two different measurement devices. We'll call them Alice and Bob. So Alice measures in some random direction and Bob measures in some random direction. And they do this completely independently. Only at the very end do they compare notes. So they look at a string, and if they measure it in the same direction, they should always get the same result 100% of the time because of the entanglement. So that's good. Now Alice and Bob share this secret key that they can use for encryption. Now if you redo it, using some sort of eavesdropper, call her Eve, Eve is trying to be sneaky. So Eve is grabbing one of the qubits, measuring it, and then replacing it. So according to classical physics, this is the perfect crime because you would never know that the eavesdropping took place. But it's not classical, it's quantum. So even though this replacement has been done, of course, the entanglement has been broken. And so now, even if Alice and Bob are measuring in the same direction, they aren't guaranteed to get the same answer. And so when they do their comparison at the end, they'll notice that some large fraction of the time, they'll get different answers. So this is mathematical proof that some sort of eavesdropping or tampering has taken place. So there's no longer trust that's required. This is actual mathematical evidence that something is going on. And so using this technology, we developed IronBridge, so it produces random numbers, but in a way that you can prove that no tampering or eavesdropping has gone on. There's a complete audit of looking at what the intermediate states were and what directions the measurements were in. And so if there was ever any doubt in your mind as to whether it was secure, you actually have this full audit. And so we're already starting to implement this on both the IBM and the Honeywell device. So this is something that's available today. This isn't years from now. We're already doing this now. So, so this is the service we're doing. So that was it for my prepared remarks, but I'm happy to answer any questions that you might have.
A question for me for the it's gonna be again like specific to the
Yeah.
last project. How would Alice and Bob would compare the answers if they're away? Like, I mean, how would they transport that? Like, that's the question
So
for me.
yeah, there has to be a classical channel set up in addition to this quantum channel. There still has to be a classical channel. So they have to feel secure that they can communicate at least something to verify each other's results.
Yeah. So like that still requires a classical.
Yeah, you still need a
channel that
classical
is
channel.
reliable.
Yeah, yeah.
What is quantum channel being used? Is it like fiber or satellite?
So fiber is a common option. So yeah, you just send photons across the fiber, but it doesn't work over long distances. Is the problem. And so the alternate approach is you can use lasers in space, and there's already these quantum satellites that are being deployed. So for example, China had this Nicias satellite a few years ago, which uses this technology.
What's long distance on the fiber?
I think it's 100,000 kilometers. It's sort of the rough order of magnitude. Yeah.
Also, I was wondering, like you showed, like you are collaborating with lots of companies. So is it like you do some sort of proof kind of experiment and show them that once you have 100 qubits, you can move to quantum, or do they actually move to quantum algorithms in the day-to-day?
Yeah, that's a very good question. So that's exactly what we do. So we work on these proof of concept type projects. So we make it very clear to them that we'll do this. We'll write a real quantum application that will run on real quantum hardware. You won't be able to commercially deploy this, but this illustrates how it would work. And so then once we do that, then we check how well it would scale. And so we say in 3 years, if we had 1,000 qubits, what do we expect? Do we think there would be an advantage to that? And so yeah, the programs that we run now have at most dozens of qubits that they use.
Do you think you can break RSA in just a few years?
It's optimistic, but so Shor's algorithm, which showed that quantum computers can do this factoring efficiently, it's an existence proof. It's not necessarily the fastest approach. In fact, there was I think it was Craig Gidney at Google just a few years ago. He improved this by like a factor of 1 million just a few years ago. He used clever mathematical technique. So yeah, it could be longer than a few years, but from the chart that I showed about the progress that we're making, so it's Honeywell keeps up a factor of 10 every year. So that means in 5 years, that's 100,000 times increase in quantum power. And if some clever young people figure out shortcuts from Shor's algorithm, then that would put us in just a few years.
With quantum power, you mean the volts, right? Like not the number of.
Yeah. I sometimes use those interchangeably. Yeah, quantum volume.
I have a question about that quantum volume that you showed that Honeywell actually that each year 10 times actually. Do you know which technology they're trying to use actually to increase that quantum volume?
So
compared
yeah,
to
so Honeywell uses the ion trap technology. They don't have a huge number of qubits, but the fidelity of the qubits is incredible. They're bragging about how many nines they can get behind the decimal place for the fidelities. And so right now they have the highest confirmed quantum volume, 1024. It's not because they have so many qubits, it's just that the quality is incredible.
But they have 10 incredibly quality qubits, so that
I think it's 11. Yeah, I think last I heard it was 11 qubits, but they're incredibly precise. Yeah.
Well, there's the other issue about more completely connected, right?
And more completely connected.
Yeah.
Yeah.
Yeah, so I've actually been really interested in Ticket because it's a really interesting way to unlock all the available options for quantum systems. So I've only been looking at your open source, well, whatever's on your GitHub. But so from this presentation, so your Cambridge Quantum, you guys have your own huge library of stuff that you guys have been building for your clients.
Yep.
Behind the scenes, using, and you're sharing some of the open source stuff you're choosing to reveal for us.
Yeah.
Right? Is that?
Yeah, so Ticket we developed both for selfish reasons for ourselves, but also for the broader community. So that's why it's open source, anyone can use it and everything. But yes, we have a lot of people working on these applications. So companies hire us, we develop this. Yeah, since I mentioned our business model, we're also kind of unique in that we keep all of the IP. So a lot of other quantum companies that do consulting, they do a report and they hand it and they go away. So the agreement that we have with each of our clients is that we write this quantum application to solve the problem, but we still own the application. We license the results to them for some length of time, and that's all negotiable. And they can use that however they wish, but we still own the application. And so every project we do, we learn more and our applications get better. And so, yeah, so for chemistry, for example, we've done about 20. And so very soon we'll be making the software available for commercial use. So companies can pay to use the software and do whatever they want with it.
So it's similar to the SaaS business.
Exactly, it's a SaaS business model, yeah.
That's really interesting. I guess I didn't do quite enough research into Cambridge Quantum.
Yeah, no, but it's understandable because, especially for the academic community, we don't publicize the commercial side because you're probably not going to hire us for these projects. But the ticket stuff, we absolutely want you to use. The only things that we ask is that if you write an article, just acknowledge us and give us feedback on how we can make it better.
And there are quite a number of students here and online and.
Yes, thank you for mentioning that. So we're hiring like crazy. So if you are interested in a position, please go to our website. We have a list of current openings. It's always changing. So if you don't see one that seems like a good fit now, check back in a month or two and we could have it, yeah.
Do you have branch in US as well?
We do. So we have a physical office in DC. We had an office in Berkeley, but we closed it because of COVID. It was basically only me, and I moved out of Berkeley. It's unclear what will happen because of this merger with Honeywell. Will we have other offices in different places? I truly don't know. In fact, I'm waiting to learn myself so I can figure out where to move next. So yeah, so right now it's not so important where you are geographically.
Are you familiar with a little startup called Atom Computing?
In Berkeley, yeah, it was some Rigetti guys that came out.
We just opened an office here. And their
Oh,
CEO was from here.
oh, this is the one you mentioned. I see. Okay, yeah.
I'm just curious.
I met them casually at a few meetups in the Bay
Yeah,
Area.
all their labs and everything are in Berkeley.
Yeah. Yeah, no, I was in Berkeley for 4 years. So we had Rigetti, we had Atom, we had Leximo, we had the LBNL labs, we had UC Berkeley. So that was quite a good place to be. Yes. Well, yeah, feel free to email me with any other questions.
Yeah, any questions from anybody online? Just unmute and feel free to ask.
Are you working with any of the airlines? Organization?
We've spoken to several major airlines. I don't think we've engaged on a project yet, but we've spoken to several of them.
We have.
Yeah,
Any other questions, either in person or online? Okay, great. Well, actually, since we're in person, we can actually give our speaker an applause. It's been a long time since I did that.
Thank you. It's been a while.
Very helpful.
Yeah, thanks.
Yeah,
Appreciate it, Mark.
thank you.
This is really very interesting. Yeah, we got some online applause too. so.